interferometer has really nice parameters. It's fast, it's high resolution, full aperture, and very high precision. However, it's limited in the dynamic range of the shapes that it can measure. It's generally limited to spherical and plano surfaces. A CGH extends the dynamic range of the interferometer to measure nearly any shaped optic while maintaining the positive parameters of the interferometer itself. The CGH enables snapshot measurements of asphere and freeform optics. In order to align the optic to the CGH, we must first understand the mechanical datums of the optic under test. In this case, the datums are defined by a plane on the back surface, defined by 3 raised pads. The in-plane position is controlled by these 2 through holes, which are precisely positioned relative to the optical surface. These features are used to mount the part and position the optical surface relative to the CGH. The test optic is mounted to the metrology platform, which has mechanical features that interface with the precision mechanical features of the test optic. The metrology platform also has optical features that interact with alignment patterns in the CGH. There are photogrammetry targets for coarse visible alignment and sphere-mounted retroreflectors for precision fringe alignment. The metrology platform is mounted to a fine positioning stage, which allows adjustment of the optical surface in all 6 degrees of freedom. Next, you'll need a CGH, or computer-generated hologram. Lastly, you'll need a fine positioning stage for the CGH. Place the CGH on the FP stage so that the hologram pattern faces away from the interferometer. In this case, we want the AOM logo to be on the left when looking back into the interferometer. While in align mode, adjust tip and tilt of the CGH until the return spots from the diffraction orders are visible. Locate the brightest return spot. This is the 0th order reflection from the planar glass surface itself. In this case, the design of the CGH indicates that the side of the CGH with the AOM logo should be tilted away from the interferometer, approximately 1 degree from the 0th order. In this case, it's the 2nd spot from the 0 order. Now, when you switch to view mode, fringes should be present in the retro alignment pattern only. Fine align the retro fringes with the FP3 stage. And the CGH is now aligned to the interferometer and will require no further adjustment. Our CGHs can be designed to project optical references in space which define the nominal location of the MP and thereby the test optic. A piece of paper or tissue can be held up to locate where the alignment references converge in space. Place the metrology platform so that the point focuses converge on the center of the photogrammetry targets. The line focuses will then converge on the SMRs, and the cat's eye reference should converge on the vertex of the test optic. The metrology platform and test optic are now coarsely aligned to the CGH.
So once we're in the neighborhood here, we can start to use the fringe feedback from the alignment patterns. And these are really nice because they provide each pattern or each set of patterns provides feedback for a particular degree of freedom. In this case, I have the pattern on the right in the middle is a vertical fine focus reference, and it provides horizontal feedback. So we can see I can adjust X a little bit and get this nice and horizontal, and that means we're in the right position in X translation. And then the 2 patterns on the right, on the top and bottom, are horizontal line focuses, and they provide vertical feedback. So we can see that I can adjust Y and have these come into near null. And then the pattern on the left in the center is also a vertical feedback. And the reason for this is that with 2 vertical feedback nodes on either side of the metrology platform, we can actually get in-plane clocking, which is required for a free-form measurement like this. So I can adjust clocking on the stage, and we see that the 2 patterns on the right are not quite vertical. I can't null them both at the same time. And the reason is that those are line focus patterns that come in from an oblique angle to the center of the metrology platform. And when they're returned either too soon or too far past their converging point, their focus point, these patterns will be asymmetric. They'll be identical but reversed, which gives some Z feedback. So we have some Z alignment by the pair of alignment patterns. So I actually have a fine Z adjustment on the CGH itself here. I can actually adjust Z, and these are nice because they the direction that they're pointing indicates the direction that the spacing needs to go. So they're pointing away from each other now. So I need to move the CGH away from the metrology platform until those are nice and null. So all of the in-plane adjustment is quite good now. The last degree of freedom to adjust is out-of-plane tip and tilt. And that is fed back by, there's a vertex cat's eye set of patterns that are created by the circular patterns in the center on the top and bottom. And I can see I just have a little bit of a return in there, so I just want to adjust tilt until those start to come better into focus. And we see as we do that, the fringes in the null actually come into focus also. And as I've done that, I've adjusted a little bit of X, so I can just come back and null that guy back out. And it's a little bit of an iterative process here to dial this in.
And once all the alignment patterns are nulled, we see that we have aligned a free-form optic using a CGH and a metrology platform with GuideStar alignment references in just a few minutes.